Hey everybody. So I want to explain ANOVA to you in this video. Now, word warning, the explanation gets a little bit tricky. So please feel free to go back, rewatch the explanation. I will try to make it as clear as I can, but you're gonna have to be ready for some thinking. So here we go. Let's share up the notes and start talking about ANOVA. Where are my notes? There we are. All right, so I'm going to assume that you watched the two sample F test video and the intro to the F statistic video, and now are ready to talk about ANOVA. So here's the idea behind ANOVA. So I'm not going to worry about these requirements yet. This is going to be relevant in a little bit, but first, just what ANOVA is. ANOVA stands for Analysis of Variance, right? It's an acronym, kind of. And what you're doing is not comparing variances. Well, you are comparing variances. But the test that you're doing is testing to see whether several means are equal to each other or not. So it's an extension of the two sample t-test, right? So you remember the two sample t-test, we would check to see if mu1 was equal to mu2, or if one was greater or less than or not equal to. ANOVA only checks not equal, and it works on any number of means. So you could have, we could check to see if 25 means are all equal to each other, right? Now, you don't just randomly do ANOVA on anything, right? You have to have some reason to believe the means are equal. So for instance, let's say you wanted to check to see if several different professions all had the same average salary, right? Like contractor and a mechanic and a plumber and I don't know, some other tradesmen kind of professions, and you wanted to see, do they all have the same average salary? Well, you would get a bunch of contractors and a bunch of plumbers, a bunch of mechanics, and you would find all their salaries, and you would do ANOVA, which we'll learn how to do in just a second here, on them to see if their means were all the same. So we're going to check to see basically if the sample means are close enough to each other, or excuse me, other way around. We're going to check to see if the sample means that we get are far enough apart from each other that it makes us think the population means are different. That's the basic idea of ANOVA. That's what we're doing. It's an extension of the two sample t-test. So it's like a multi-sample t-test essentially. Now, you might have noticed that at no point in there did I mention standard deviation or variance. Here's how we are going to do the test. We're going to make groups of each of those. So here, let's come down here. Here I'm explaining sort of the technical details. I really want to do, I want to explain with an example. So here's my example. So here we've got supermarket shelves, right? So this is in a bakery, and we got the top shelf in the bakery, the middle shelf in the bakery, and the bottom shelf in the bakery. So they've got three levels of bread and cakes and whatever in there on the shelves. It's a reasonable first assumption to think that, well, it's all the same bakery, they probably all have the same average sales on those shelves. And so we're going to do a test to see if that's true or not, right? So we're going to find, we got the sales from the top shelf, sales from the middle shelf, and the sales from the bottom shelf that we're gonna compare, right? We want to see if the average sales on the top shelf, middle shelf, and bottom shelf are plausibly equal or not, right? If it's plausible for us to think they're equal or not, and if it, depending on what the results are, that might make us more or less inclined to be careful about where we put things on shelves, depending on what we're trying to sell, et cetera, et cetera. So, right, this is semi-important information for us to know how to stock the shelf. Now, obviously, in practice, you have a lot more variables that go into this, but for now, I just want to explain the basics. So what we do is we make groups for the top, and then top, middle, and bottom, right? So here's the top. We're thinking of this right here, these six sales as one set of data, right? The one sample. Same thing for middle, and same thing for the bottom, right? So what we have is 3 samples. Each of those samples in this case has 6 items in it. So what we're going to do is the following. We're going to find the mean of the top, the mean of the middle, and the mean of the bottom, the sample means, of course. And we're going to find the variance. We're going to take those 3 numbers that we got, the means, and we're going to throw them into one set, and we're going to find the variance of that set, because that will tell us how far apart they are, right? Because that's what variance measures. Variance measures how spread out a set of data is. So if we make a set of data out of our sample means, the bigger the variance of that set, the more spread out they are, and therefore the less likely they are to all be equal or to have equal population means. That's one. That's going to be the numerator in our F statistic. The denominator is the average variance of each of the groups. So in other words, we're going to find the variance of the top, right? So we're going to find the variance of these 6 things, and the variance of the middle, and the variance of the bottom. And then we're going to average those. We'll take a weighted average based on degrees of freedom. So it'd be, each of them would be 5 here, so it'd just be a regular average. We're going to take a weighted average of those. And the reason we're doing that is the following. The idea here is the more variance you see in the denominator, so in other words, the more variance there is within each of the groups, the more you would expect the means to vary within each of the groups. So if the numerator has significantly greater variance than the denominator, it means that we think the population means are noticeably different from each other, and they are more different than you would expect based on the variance that we see in the denominator. That's the idea of ANOVA. I don't know if you guys are familiar with the phrase signal to noise ratio. It comes from electronic communications, as far as I know, radio waves and stuff. With the idea being that what you're trying to do when you transmit an electronic signal is you're trying to get the receiver to pick up the signal without the static that you get from the noise masking it too much, right? So that's why, like, if you see old style radios and you're like tuning manually between frequencies, there's static and crackling between where you get the signals. And so the idea is you want to detect the signal and ignore the noise. So the reason I bring that up is that what we're doing here is the numerator is our version of the signal. How far apart are the sample means? And the denominator tells you how much noise you have. How spread out is each group, or how spread out are the groups collectively, is really what I'm trying to say there. And the more noise you have, the harder it is to detect the signal in the numerator. That's why we're doing a 2-sample F test, where the numerator is the variance of the sample means, and the denominator is the variance of the samples themselves, the average variance of the samples themselves. So that's my explanation for what ANOVA is. It is a formula we use essentially to detect the signal from the noise. And if there's too much noise, the signal doesn't come through and we can't detect a difference. If there is enough signal, like the numerator the means in the numerator are far enough apart compared to how noisy the denominator is, then we can detect it, and that'll make us reject the null hypothesis. So that's ANOVA. Now, before you get too scared and turn off this video and just give up on life entirely, we're not going to do any of that manually. I've done ANOVA by hand before, and it is awful. it's a lot of plugging and chugging, and we're not gonna do that. There's an ANOVA button in your calculator that we're going to use to get all these things we wanted to just immediately jump straight to the F statistic and the p-value. Not a problem. However, the thing about ANOVA is it is very sensitive to some assumptions that you have to make in order to do what we want to do. So each population has to have the same variance, right? So we're trying to do a two-sample F-test here, essentially. That's not exactly why these all have to have the same variance, but it's related. So all your populations have to have the same variance. We're going to check that. We're going to check to see if that's plausible or not. Each of the samples have to be independent of the others. This one is a thing that we probably can't check, because if the samples are dependent or independent is really up to the researcher to do good data gathering on. So we're going to punt on this one most of the time and just say, we're just going to assume that they have to be independent. Now, you can make some assumptions. So for instance, the samples have to be independent. So that example that I gave you earlier with the bread, this probably fails that test, right? This is top, middle, and bottom shelves in the same bakery, right? It's probably not the case that this number and this number are independent from each other. If this number is bigger, most likely that one will be too, right? So these probably have an effect on each other. And when you are relating your conclusions, that should be front and center. You should absolutely say, we're not so sure about this this conclusion. That doesn't necessarily mean that all of your information and everything you've done is invalid if you don't quite meet the assumptions, but it does mean that you should put some caveats on your conclusions. So we'll talk about that a lot more later. That's going to be the focus of what we're doing most of the time, because the actual ANOVA, like the actual operations for this, very simple. It's literally put it in the list, hit the button, there's your p-value. Like that's it, right? Make your conclusion based on that. But we really have to concentrate more on whether our conclusion is reasonable based on how well we met these assumptions. So we can test this one. We can test to see whether something is from a normally distributed population, right? We can do a QQ test with that, or a QQ plot, excuse me. We did that when we were doing two-sample t testing, or paired t is where we're introduced it. We can't really check independence. What we can do is make some arguments one way or another, but there's not like a formula for this one. You're just gonna have to reason your way through these. And checking to see whether the populations have the same variance, well, that we can totally do, right? Because we literally just learned the two-sample F-test, which tests to see if two populations have the same variance. So we're gonna do that for this. So let's go all the way through an ANOVA test. I'll show you how it goes from beginning to end. We'll check all the assumptions, write some conclusions, or write a conclusion, and comment on our assumptions and how well we think they were met, which is very important. And then that'll be ANOVA. So here's what we've got. Your hypotheses always look like this. Yeah, so we've got mu1 equals mu2 equals whatever through mu k. So however many populations you are doing, you can remember this works with any number, right? So this k can be as big as you want. Now, of course, if you have many populations, it becomes more and more likely that you'll get like population 2 and population 17 turned out to be different from each other. And it becomes easier to get a type 1 error where you end up rejecting something like that just from random chance. So in practice, you don't necessarily want to make this too large. because you can have you can get some extra type 1 errors if you're not careful. So the null hypothesis is the means are all equal. The alternative is at least one's different from the others. Now, that sort of begs the question, like, okay, so I've got several means, and this number I got tells me that one of them is different. Which one? Like, which one is different from the others? And that gets into what's called post hoc analysis, which we're not going to worry about just for simplicity. So I figure if you ever have to do an ANOVA test, like for your job, for instance, like, so for instance, psychologists end up doing ANOVA tests quite a lot in their work. So you'll end up doing, you'll end up learning a lot more about ANOVA. And so there's multi-factor ANOVA, two-factor ANOVA with, what am I looking for here? Interaction effects. We're just doing the very basics because ANOVA is complicated enough as it is. So what I really want from you guys is to be able to do the basic ANOVA and check these assumptions. I'm not going to worry so much about the post hoc analysis, but I will put a little extra credit on test 3 if you can do some post hoc analysis. So I'll talk about post hoc analysis a little bit later when we're talking about the assumptions, how to tell whether they're different from each other. It's not particularly hard. There's nothing all that complicated about it, but it does complicate an already complicated subject, so I'm not going to worry about it as part of the base, or as part of the base of what we're doing. Okay, so I need to talk a little bit about some terms that we're going to see. MSB and MSW. Remember the way I described this was MSB, or excuse me, the F statistic that we make for ANOVA is the variance of the sample means in the numerator and an average of all the sample variances in the denominator. And that's what MSB and MSW are. MSB stands for mean squares between. So that is mean squares. You want to think of mean squares as variance. So this is the variance between the groups. This is the average variance within the groups, within the different samples. So between the samples, within the samples. This is the signal, that's the noise, right? The more variance you get within the groups, the harder it is to detect variance between them. Okay. Yeah, that's what MSB and MSW are. Your calculator uses entirely different terms, which we will see in just a second. So I want to kind of run through this just to show you, like, just to get you used to doing an ANOVA test, and then we'll talk about what it all means. So what I'm going to do is I'm going to type all this in to the calculator, and I would encourage you to do the same. And I'm not even going to pause the video while I do it to give you some time where you can do that. So as always, the more different kinds of learning styles you can incorporate into your learning, the better it will stick, even if it's not your preferred learning style. So kinesthetic learning, even if you're not a kinesthetic learner necessarily, it will still help you some to do some activity while you're trying to learn something. So that's what we're going to do. So I'm going to flip over to the calculator here, and we're just going to type stuff into it. So I'm going to go to the lists, stat, edit, go to lists. So I've got all my lists in here. Pardon me. This is from something we did earlier. We're going to go to memory, clear all the lists, and then go back to stat and edit, and here they are. So here's what I'm going to do. Each of the lists is going to be a different sample. So this is going to be top, middle, bottom. So I'm just going to type in from the tables that I've got in the notes, those things. So top, 50.2, 50.7, 6, 61.4, 64.7, and 58.8. Middle, 63, 68.1, 59.3, 65.5, 61.6, and 58.4. It's a great opportunity to work on your 10 key skills as well. 0.8, 56, 51.9, 53.3, and 58.3. Okay. So I'm gonna go, let's go make sure that this all matches up. 3.7. Good. 5. Good. I know this can seem a little tedious and like a waste of time to check all your data, but let me recommend that you do that whenever you type in a bunch of stuff, especially on a test. And tests are when it is hardest to convince yourself to do this, and also the time when you most should. It's definitely worth it to go back. Like, for instance, it would be really easy if I just, to have, let's say I didn't type the 1, right? This data is significantly different from the data I had, the correct data. And I'll get a much larger variance in L3 than I would have otherwise. And that's going to mess up my whole analysis. And so not so much because you'll lose points on a test for typing in stuff wrong. Like I'll dock you a point for a typo or whatever. But the problem is that what ends up happening is you reach the wrong conclusion. And so so you get conclusions that don't make any sense a lot of the time. So that's why you want to check your data, is not so much because you'll lose points directly for the typo. Well, like I said, I'll knock off maybe a point if you just have the wrong number in there. The problem comes when your conclusion doesn't match up with like your confidence intervals, and like you just get all these mismatches and errors. So you can avoid all of that by spending literally 30 seconds looking over your data. So so just look over your data. It's worth the time. That said, here's how you do an ANOVA test. There is an ANOVA button. I'm just going to go to Stat, Test, and ANOVA. Stat, Test, ANOVA. There it is. Bam. And then I have to tell it which list I put the data in. We put them in L1, L2, L3. So we're going to do L1, comma, L2, comma, L3. So L1, comma, you got to have the commas. L2, comma, L3. Close parentheses. And then it's going to explode with a bunch of information. And I'll show you around the information. So there it is. All right, so it says one-way ANOVA. Like I said, there's other kinds of ANOVA. There's two-way ANOVA. There's ANOVA with interactions. There's lots of stuff. We're not going into any of that. We're just doing your basic one-way ANOVA, no post hoc analysis. So they call between and within factor and error, which is common. This is not a weird thing that your calculator or book is doing. This is, some people call it between and within, some call it factor and error. I've seen both ways in multiple places. So remember that what we had was MSB and MSW, major F statistic, right? So that was this. F is MSB over MSW. MSB is MS factor, and MSW is MS error in your calculator. So here is MSB is this thing, 122.65. That's the numerator. That is essentially the variance of the sample means. MS error is 12.86. That is the average variance within the samples, roughly. When you make a ratio out of 122.65 over 12.86, the thing you get is 9.53. And then if you were to do FCDF with that, you would get a p-value of 0.002. That's what it's saying here. Let me explain the degrees of freedom a little bit now. Yeah, I will. So SS, you don't even have to worry about SS necessarily, but basically this number, the SS over degrees of freedom, this stands for sum of squares. Sum of squares over degrees of freedom gives you mean squares. Same thing here. Sum of squares over degrees of freedom gives you mean squares. So 245.3 divided by 2 is 122.65. And 192.96 divided by 15 is 12.86. The way you get these numbers of these degrees of freedom is actually n-1, sort of. So remember, for the numerator, that's factor, that's MSB. What we did was we took the sample means and we made a set out of them and found the variance of those. Well, we had 3 groups, one sample mean from each group. 3 minus 1 is 2. That's where this 2 is coming from. For the denominator, what we did was we averaged all the variances together. Well, each group had 6 things in it. Those 6 things give us 5 degrees of freedom, and we have 3 groups. So 5 plus 5 plus 5 is 15. That's where those are coming from. I will not ask you much about how to calculate degrees of freedom, right? But that's where those things are coming from. Don't even worry about the sum of squares. There's a thing that you can do with sum of squares to sort of check if your data is matching up, but I think it's silly to check your calculator. I'm just going to trust the calculator has done it right, and again, check your data. The thing we care about here is p equals 0.002. This is our p-value, right? And so this is less than 5%, so it makes us want to reject the null hypothesis. That's the top line number that you're looking for is that one. All right, so here's where we're at. Okay. Products in this supermarket are displayed on one of 3 levels. We're going to test to see if the sales are different depending on the level they're on. That's what we've done. We did this, right? Put all our data in. We were careful about it, checked it. There's a lot to check, so do be careful. We go to stat and tests and ANOVA, and then we tell it which columns we used. We used L1, L2, L3. You can use other columns if you want to. And in fact, sometimes it'll be to your benefit to use different ones, like if you want to keep data in some of the other ones. So don't get married to L1, L2, L3, but that's the default. And then we see this set of screens that we have. And our p-value is this thing, 0.0021, right? Significantly smaller than 5%. All right, so let's do all this. I'm going to write appropriate hypotheses, determine if we should reject the null hypothesis, and write the conclusion. So if you remember from our hypotheses, here's how the hypotheses go. Null hypothesis, all the means are the same. So mu sub top is equal to mu sub middle is equal to mu sub bottom. It's very tempting to do like mu1, mu2, mu3. Let me encourage you not to do that, right? Using numbered subscripts like that makes it harder to follow everything you're doing. Use instead descriptive subscripts. That makes it much easier to follow what's going on. I know there's a little bit more writing, but it's worth it. Alternative hypothesis. Not all the means are equal. You could write this as one or more of the means is different from the others, if you would like. However you want to say it. But the alternative hypothesis is always the same. Just they're not all the same. The reason you don't want to write this in terms of equations is it could be that these two are different, or these two are different, or top and bottom are different, or they're all different, right? You don't want to have to write out every single combination, right? It's way easier to just put it in words. So here's how I would write this ANOVA test. F approximately equal to 9.563. I forgot what it was. 5.3. P approximately equal to 0.0021, less than 5%. Right? So this is what I'm kind of looking for from you on a test. You don't have to write down every keystroke. You don't have to write down MSB, MSW, all the details in the middle. I don't care about any of that. The thing I care about is p-value and your conclusion, and as we're going to see in a little bit, checking the assumptions, which are not going to work out very well for this. So P-value is this, so we're going to reject the null hypothesis. So let's write a conclusion. Our data suggests bakery sales are not equal for all shelves. Right, which is a perfectly reasonable conclusion to come to. You would expect that the ones people are looking at more are going to sell better. But yeah, so there you go. That's how we would write a conclusion. Now, let's talk about what assumptions we needed to make for that. So let me go back to chapter 13 here. So when the assumptions aren't met, ANOVA doesn't work as well, right? So we should check our assumptions as best we can. So here's our assumptions. Each sample has to be randomly selected from a normally distributed population. Each of the samples have to be independent of the others, and each of the populations have to have the same variance. So one at a time, here's what we're going to do. We're going to do the randomly selected from a normal population. Now, we can't really do this, right? That is dependent upon the researcher doing a good job of random selection. We can argue that we didn't get a very random selection in this time because it's very specifically picked items for those for the shelves. What we can do is we can check to see if each one is from a normally distributed population, which, if you recall, is QQ plots. So what we can do is we can do a QQ plot for each one, right? We can do a QQ plot for the top and one for the middle and one for the bottom and see how they all work out or see how they all look. So that's what I want to start with. I'm going to start by making QQ plots for each one. So let's go over to calculator and I'm going to go to stat plot and we're going to make a QQ plot in plot 1. Right, so I'm going to go to plot 1. The one we want is this guy. That's the QQ plot. Data list cell 1. We're going to go back and change this a little bit later. And then we're going to go over to y equals, make sure we've got everything right. Yeah, it all looks good. Plot 1, graph. We're not going to see very much, so we're going to go to zoom and number 9, zoom stat. There we go. And what we're looking for here is that data pretty straight, or does that basically follow a straight line? And yeah, totally. This is straight as a string as far as we're concerned. That's fantastic. So we're going to do the same thing for L2 and L3, see how those look. So I'm going to go to stat plot and change that data list to L2. See what the graph looks like now, and we're going to zoom 9 again. Yes, still very straight. This is as straight as things get with QQ plots. Like, you're never going to see much straighter than this. Last one, we're going to go to stat plot. Change this to L3. Graph, zoom number 9. Yes, also this is totally fine. I know there's a little bit of a jog in the middle. It needs to be much more severe than this for us to want to consider this as not plausibly normal. So this data passed that test with flying colors, right? So we're definitely confident about the assumption that the data is normally distributed. We're not super psyched about the randomly selected part of it because we don't know how the data was gathered. It doesn't say in the problem, but we're just going to ignore that one because we have no way to check it. Right? We're going to have to rely on the researcher having done a good job. All right, the second assumption that we need to check is each sample independent of the others? Now, given the way it was described, probably not. Right? It's probably not the case that the samples were independent because they come from different shelves in the same bakery at the same time. And so we would expect that if one had higher sales, then the others would have higher sales as well, because that probably means more people came through. So we don't actually know how the data was gathered, but I'm very suspicious of this second assumption. There's really no math we can do that's gonna check it. Third one that we need to check is each population has to have the same variance. We can check this. Now, there is, so in general, you do 2 sample F-tests to see if the variances of 2 things are equal. So what we're going to do is we're going to check the variances of the ones that are farthest apart, right? With the idea being that, here, let me draw a picture. If I have, let's say I have 3 sample variances, right? So I have sample variance 1, 2, and 3. If I can say that 1 and 2 probably come from populations with the same variance, that doesn't tell me anything about 3, right? Same thing, if I can say 2 and 3 probably come from populations with the same variance, that doesn't tell me anything about 1. However, if I can say that 1 and 3, right, this guy and this guy, come from populations with the same variance, that suggests that 2 must also come from population with the same variance, because it's kind of sandwiched between the 2, right? So if these 2 have equal population variance, then this one must also. So that's the idea. We're going to do a 2 sample F-test on the variances that are farthest apart, on the samples that are farthest apart. That's the idea. So we don't have to do a million 2 sample F-tests, just a couple of them will do it. So, excuse me, not a couple, just one will do it. Because remember that for our assumptions, we need them to all be the same, right? Each population, so all the populations have to have the same variance. So we really only care about the ones that are farthest apart. Like if any are going to be different, it'll be those 2. So what we need to do is we need to go figure out which populations or which samples have the largest sample variance, largest and smallest sample variance. So what we're going to do is we're just going to do 1 variable stats on each column, or on each list, because we've got all our data in here, right? So there's our data. I'm going to do 1 variable stats on L1, 1 variable stats on L2, 1 variable stats on L3, and I'm going to write down all the sample standard deviations. So 1 variable stats, L1, not a frequency list. Calculate it up. That variance is 3.95. So let's go write that down. We have sample 1. It wasn't called sample 1, it was called top, right? So yeah, I'm gonna clear all this. So we got top, S equals 3.95, middle, bottom. Find those. All right, let's go find those real quick. Calc 1 variable stats L2. That one was 3.69, 3.70 for rounding properly. S equals 3.70. All right, those are just a heads up. Things have to be pretty far apart to be able to detect them being different, especially with sample sizes this small. These are not nearly far enough apart. Do the same thing for the bottom, stat, calc, 1 variable stats on L3. And here we're getting 3.05. That one's a little more different. S equals 3.05. And in each case, N was 6. Right, that's the information we're going to need to do a 2 sample F-test. So the 2 that are farthest apart are top and bottom. So I'm going to do a 2 sample F-test on the top and the bottom. And here I'm just checking to see if they are equal to each other or not. I don't have a specific agenda about one being bigger than the other one. All I want to know is, are they equal or not? So I'm going to go back to calculator. I'm going to do stat tests, 2 sample F tests. we have data actually, right? I don't have to even use, you could do stats for sure, right? We found all the sample standard deviations, but I can just do data here because we have them. And it was top and bottom, which was L1 and L3. And we are checking to see if those things are equal or not. So let's calculate it up. And we get a p-value of 0.58, so 58%. Definitely do not want to reject the null hypothesis, right? So I suppose I should have backed up a little bit. I did this a little too fast instead of going through all the things we're doing. So my null hypothesis here for this test is that sigma sub top squared equals sigma sub bottom squared. And my alternative hypothesis was that they were not equal. Sigma sub top does not equal sigma sub bottom. We did that test, right? That's the test I literally just did. We get a p-value of something huge, 0.58, right? So that's a really big p-value. That makes us think that we are not going to reject the null hypothesis. So that means that we think the null hypothesis is true, or at least we're willing to believe the null hypothesis, right? So, or we don't have enough information to reject it really. So that means that we think that the population variance of the top shelf and the population variance of the bottom shelf are equal. Therefore, population variance of the middle shelf also equal. So we think that the population variances are all equal. And so that assumption is met. That one's totally fine. All right, that's all the things we did. So there's really 4 things that we're checking. Well, okay, there's 2 things that we're checking and 2 things that we're kind of ignoring or maybe making an argument about, right? Random selection, normally distributed population. So random selection we can't check, normally distributed population we can with QQ plots. Independence of samples, we can make an argument, but we don't know about the details of how this data was gathered, so we kind of have to leave this one alone too. Populations have the same variance. That one we can check. We do 2 sample F test on the variances that are farthest apart. Okay. So here we go. Right, here's those QQ plots that we made. These are the same ones that I made earlier. These are all nice and straight. No problems here. This looks fantastic. Here's that 2 sample F test we just did. Right, same thing we just got, p-value 0.58. Absolutely fantastic. Never going to see better data than this. So are our ANOVA assumptions reasonable? It's debatable. Certainly the ones that we calculated looked fine, right? We're confident that the data is from normally distributed populations, and we're confident that the population variances are equal. There's arguments to be made about the independence of the samples, right? I would argue they're probably not independent. And it's not necessarily true that they were randomly, that the data was randomly gathered. So what you want to do is something like here. Let me, I'm going to pause the recording for a second. I know I've been going on for a while now. But I'm going to pause the recording. I'm going to go get the review packet for test 3 because I want to show you what I wrote there for those. Right, it's kind of lengthy, so I'll be right back. Okay, let me show you what I wrote for this. I'll show you the setup. Here's the idea. You've got different amounts of hours awake. I believe these are for doctors, right? So different amount of hours awake for a variety of doctors and number of errors they make on some sort of test or in surgery or something like that. And so more hours awake, each set of hours awake is a different population. The reason I bring this up is the following. Here's me checking the QQ plots, right? Good, 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 bad. And then we do, I do the other ones, right? So here's the 2 sample F tests, p-value of 0.3023, totally fine, right? 2 sample F test checks out. So My answer to, are the assumptions reasonable, is something like this. I'm not convinced of the normality, right? I'm not convinced this is normally distributed. We might have to make some arguments about whether it's reasonable to think that this is normally distributed. This was some sort of test, so maybe we know just from giving this test a bunch that the answers, the answers population-wide are in fact normally distributed, and we just got a weird sample. But barring that, maybe we don't know that. If that's the case, then a thing that we might want to do is toss this data out and do the analysis on just L2, L3, L4, right? See if those are different from each other, or see if those see if that changes our results. Once we've done that, 2-sample F test looks good. For the samples to be independent, we would have to check, right? We would have to know how the data was gathered for us to make a conclusion on that. So we're basically going to punt on that unless we know more about the results, or unless we know more about the research methods that somebody used. So basically, we have a couple of, so here is my final conclusion, right? Of the three assumptions we needed to check, about 2.5 of them were reasonable, right? Random sampling, independence, equal variances, normality was questionable. If we can work around the lack of normality, then an ANOVA test is appropriate. Now, the p-value that we ended up getting here, I don't remember what it was, but it was quite small, I think, right? So p-value is tiny. With a p-value that small, maybe it's okay that some of the assumptions are not necessarily pristine, right? This definitely seems to indicate that there's a difference in the results, or that there's a difference in means. So don't just throw out your answers immediately. Don't just throw something out just because one of the assumptions was maybe violated. See if you can work around it. See if you can make some arguments about why it's okay in this particular case for this assumption to be maybe not perfect, right? Maybe the fact that this p-value is so tiny kind of mitigates that problem. But don't just go into a ANOVA test thinking, oh, my answers are everything's perfect or I throw everything out. No, no, no. It's always going to be some gray area. Real world data is messy. It's never going to come out nicely. So what you have to do is think about it. Is it reasonable that this assumption that we needed is true? If it's not reasonable, say so. If it is reasonable, say so, right? Defend your position either way, but don't just reflexively say it is reasonable because otherwise I can't do the test. That's not a good reason. It's okay to have problems with your assumptions. Almost every real world test that involves some sort of statistics has some kind of problems with it. Almost always with getting a representative sample. But aside from that, there are, like, don't be afraid of messiness when you're discussing your whether you've met the assumptions or not. Sometimes you won't be able to meet them. It's okay to just say, we didn't really meet this assumption, but here's why we think that's all right. Or we didn't really meet this assumption and our p-value is really close, so we're not very confident of our conclusions, but here's what we got, right? Don't shy away from presenting what you got, even if the assumptions are a little bit messy. So that's really what I wanted to say there. One of the big problems that students often have with statistics is not being comfortable with uncertainty. And in ANOVA, once you start talking about how valid your assumptions are, that's when a lot of uncertainty really creeps in. And this is where I really want to start doing that, is because ANOVA itself is very sensitive to assumptions. You really want to check them, and you really want to be honest and straightforward and upfront about how well you met them or not. And when I say you met them, I don't mean you literally, right? How well the researcher met them, right? You're just doing the analysis. It's not like you're going to go to jail if you if you botched your ANOVA assumptions. But be honest about them. Be honest about, like, this sample's really small, and so I'm a little bit not that confident about how this came out. And The data wasn't all that normally distributed, and so I'm a little bit concerned. But we met all the other ones nicely, and our p-value is tiny, so I think we've got something here, right? That's an okay thing to say. All right, I'm going to leave it there. I can go on and on about not being afraid of uncertainty and being honest about how well your assumptions were met and all that stuff. But I think I've made my point. So yeah, don't just blindly say we met all the assumptions or we didn't meet this one, so we should throw everything out. Live in the gray area. That's where everybody in statistics lives, is in the gray area in the middle. It's rarely black or white. All right, and with that, I'll stop sharing. And I think I'm going to leave you to work on your ANOVA, and come see me, of course, on Wednesday and or Saturday if you are having any trouble. I'll be there to help you. I'm sorry I've been absent on the last couple. One, my computer was broken, and the other one, nobody showed up. Yeah, so I will see you guys around. And yeah, with that, I'm going to go ahead and end the video here.